Hi, let's look at the various kind of non-relational data stores that we have. The first one in our context is a document data store. As the name suggests, document data store, it simply stores a document corresponding to a particular key. This document can be in any format. It can be JSON, YAML, XML, text, or binary JSON. Now these documents can have different schema. There is absolutely no constraint from the database side to enforce a particular schema. However, the important thing to note here is that if you have different schema for different rows in the same document store, your application needs to be written in such a way that it can interpret and understand the different documents or the different schema of different documents that it is expected to process, which is why in all practical scenarios the developers still come up with some sort of a schema and they try to use that schema for the document, because otherwise you will have to do a lot of if else and many other cases in order to find that, oh well, if this schema is present or not, if this key is present or not, and then we have to process like this, otherwise process like this. So in order to avoid all those programming issues which can relate to or cause various kind of bugs, for all practical purposes there is some notion of a schema that is generally added to the document data store. Now this schema can be a constantly evolving schema. For example, you could run with a particular schema for, let's say, a couple of months, and then your application changes and now you're adding a few more fields to your schema, and that is perfectly fine. Your document data store can contain documents which are belonging to both these schemas, but then from a application development point of view, your code needs to be written in such a manner that it can work with the previous schema as well as the new schema. And as your application keeps on evolving, there could be more schema could be updated and added. Now all of this is simply at the programming layer or the application layer. The data store itself does not enforce any schema. It does not mandates any structure to the document that it has to be there. These documents are retrieved by a key, just like relational databases in document data store, or pretty much in any data store that we talk about. There is a notion of a key which uniquely identifies a particular document in that data store. Now these keys are often hashed to help distribute data evenly. In this case, a key can be an automatic key or it can be specified by the user. It really depends on what is the exact document store that you are using. Most of the cases, the documents are indexed for fast lookup and for also providing some sort of a filtering or querying option based on the attributes present inside the document. In certain other cases, there are in-place updates happening, which means that taking this example, if you want to update the quantity of product that has been ordered, you don't need to update the entire document. You can simply update the quantity and be fine with it. A very good example of a document data store is MongoDB, which is again a very popular tool and used by a lot of developers across the world. The other kind of data store that we are looking at is a columnar data store. Now in columnar data store, it still stores data by rows and columns, but in this case the columns are divided into groups which are known as a column family. And the columns in a column family are usually logically related, and they are retrieved, inserted and manipulated as a unit. This kind of a data store is popular in analytics kind of application, wherein there are many column families associated with a particular key, and there is no requirement of these column families being present for all the rows. Rows can be sparse. A row can have one or many or none of the column families that are present in that particular data store. New columns can be very easily added into the family, and the read-write operations in this kind of a data store is atomic by column family, and in some cases some databases also allow them to be atomic by row. Column family, in a column family, all the data is within a column family are stored together in the same file with a specific number of rows in each file. Now with large data sets, this approach creates a performance benefit by reducing the amount of data that needs to be read from disk when only a few columns are queried together at a time. So this kind of a use case is very popular in analytics application. A lot of analytics based application were built using these kind of data stores, and H-based Cassandra are very popular example of columnar data stores. Next one, we'll look at KeyValue data store. A KeyValue data store is essentially a large hash table wherein the lookups are O1. These kind of data stores can perform query, insert, delete, and scan of the keys. And all of this is happening on the keys. There is no operation that is available on the value. You cannot really query or filter on the value. And the reason of why this data store behaves like this is similar to why would anyone need a hash table. Hash tables are known for their very efficient lookups and very fast writes. So you can imagine any application that needs to cache something for a relatively short or a longer amount of time span and needs very fast access on it, typically ends up using such kind of a data store, and Redis, Memcache are very popular example of such kind of data stores. In this case, the values can be pretty much any data structure. It can be strings, bitmaps, list, sets, or even geospatial index. The data store is not bothered about what is the nature of data that you are storing in the value, because ultimately it is your application that is going to read this value and decode this value to make sense out of it. So that's how we end up using a KeyValue data store. The next kind of data store is a graph data store. Graph, as we all know, is a data structure that contains nodes and edges. So nodes in this particular case are the entities that we saw in our relational database example, and edges represents the relationship between these entities. And these edges can be unidirectional or bidirectional. It really depends on the application that you are building. Now, if you really think about it, it is totally possible to represent this kind of a relation in a relational database as well, the relationship between entities. However, a relational database is optimized for row by row access to the data. And if you are, for instance, fetching a row with ID 8, that also depends on row with ID, let's say 6, and that row with ID 6 in turn depends on row with ID 19, and so on and so forth. Those kind of data retrieval becomes really slow in a standard relational database, and that's why the need for a specific graph data store arose. Now, in this example that we are looking on the right hand side of screen, this shows a graph that can be thought of using Twitter as the use case. So there are 3 or 4 different entities. There's a user, there's a tweet, there's a link, and there's a hashtag. Now, user can post a tweet, and tweet can mention another user. The tweet can also have tags. So if you are using Twitter, for example, you can search all the tweets by a hashtag. You can search all the tweets by a user that is mentioned in those tweets. And these kind of queries become very easy if you are using a graph database, because you simply have to perform graph traversal and find out the required nodes that are that follows that particular query criteria. And there are few types of graph data structures that are very common. There's a social, there's intent, there's consumption, interest, and mobile. And all these all these types of graphs are very commonly used in many applications. For example, any social network that you see can essentially be represented and stored as a social graph. Similarly, there is an intent graph wherein based on certain actions, we try to understand what is the actual intent of the user. And some of the very popular examples of graph data store are Neo4j and dgraph. Next in line comes the time series data store. The time series data store is optimized for storing values by time. Now this is a specific use case because if you look at certain use cases, for example, telemetry data, if you are so taking two very specific examples, for example, any IoT related data wherein you are having sensors that are streaming values, sensors that are emitting values, and those values have a timestamp, you would look at this data and you will find that this data is relatively small in size. They are rarely updated because once you have a sensor value coming, you don't really update that. And there is no delete or that is usually performed on this kind of data. And if a delete is required, the deletes are usually bulk delete, because if you identify that the sensor is faulty, you would want to erase all the data that the sensor has emitted since the time it was diagnosed as faulty. You wouldn't really go and remove one particular timestamp value from that sensor. And similarly, in other cases, you can think of this as the metrics that are shown for, let's say, your compute resources that you are using in a virtual machine. Those resources, those metrics are also telemetry data and can be stored very efficiently in time series data store. The real power of these data store comes because they are optimized for queries described in terms of windows of time, which otherwise would be relatively slower if you pick up a standard relational database or any other kind of data store. I mean, they all can support this kind of a data structure and store and retrieve and do all those things, but time series databases are specifically designed for that, and that's what makes them more useful and more powerful in these kind of situations. Very popular example are Timescale DB, OpenTSDB, and InfluxDB. The other kind of data store is an object data store. Now this object data store is optimized for large blobs, and they are typically stored as files in a file system that can be logically that file system might be logical or physical, and that these kind of data stores are used to store, for example, images, video, audio, disk images, and so on. So any large data that you can think as a blob is stored typically in an object data store. Now the question arises that when can one use a relational database, whereas when can someone use non-relational databases? And honestly, in any production application or in a large scale application, you will find both of these kinds of databases coexisting for specific use cases. For example, in most scenarios, you have some sort of a user that is signing up for a service, and the user data is going to be pretty structured. It's going to be pretty related in terms of which user resides in what city and so on and so forth. And those are the kind of data that you would want to put in your relational databases. And then there are other sorts of data that you would put into non-relational databases. And the choices that bring us to this decision depends on the scalability and performance that we are expecting. It depends on how much structure is present in the data. So if you are really looking for a very highly scalable and performance system, that can store semi-structured data, then definitely non-relational databases are the way to go. The other advantage of non-relational databases is that because of their semi-structuredness or schema-less approaches, they are very agile. Your application could keep on evolving without really the need to change your database every time or the schema every time. And there is no silver bullet answer to the choice of relational or non-relational databases. It usually is a mix of all these factors that we have just seen and discussed, and the nature of application that you are building. If you have to take a rule of thumb, I think most of the time it's advisable to start with, let's say, a relational database and assess your application in the, like, for example, how is your application's data requirement going to be in next 6 months, in next 1 year, in next 2 years, and so on. And if you see that there are certain cases wherein the structure might change or the scalability, like you could quickly end up into terabytes and petabytes of data, I mean, those are the cases wherein you would want to store them in non-relational databases.